The chain rule is our last differentiation rule, and it applies to compositions. Before we get into it, though, I want to remind us of the concept of a derivative. The derivative of a function is a function that gives the slope of a tangent line at a point. This is kind of an informal thing that I just said. Let's take a step further back and talk about what a slope is. Y equals, say, 2x plus 3. The slope is 2, or we can think of it as 2 over 1. And remember, slope is change in y over change in x. And as you know, what a slope of 2 means is that if x changes by 1, then in this case, y changes by 2. Now let's consider f of x is equal to x squared. Actually, I'm going to call it g of x because I'm going to set something up here. Then we know that g prime of x is 2x, which itself isn't a slope, but for any particular value of x, we can put a number into g prime and get a number out. Like for instance, if x is equal to 0, then we have a slope of 0, and we know that that corresponds to a horizontal tangent. If x is equal to 1, then the slope is 2. And the tangent line here, when x is equal to 1, has a slope of 2, which is going to be a change in output of 2 for every change of input of 1. When x is 2, g prime of x is equal to 4. And so when x is 2, we see the tangent line has a slope of 4. And that's like if x changes by 1, then the output changes by 4. Here's what I'm getting at. As the input changes, the output changes, right? And the rule that tells us how the output is changing is 2x, because 2x is the derivative of x squared. And so I want you to think about an output changing as an input changes. So another way to characterize a derivative is how the output changes as the input changes. Now let's consider f of x is equal to the sine of x. Then we know that f prime of x is equal to the cosine of x. And for any particular value we put in place of x, f prime will tell me how the sine function is changing. So for instance, when x is 0, the derivative is 1, and you can see that the tangent line would have a slope of 1. Or when x is pi over 2, the cosine of pi over 2 is 0, and you can see that's a horizontal tangent, no change in the output for a change in the input. But again, our derivative is how an output changes when the input changes. So as x changes, the slope changes. Why didn't you tell us this before? Well, I kind of did, but I'm telling you now, chill. All right, now look, I want to consider now a composition of functions. F of g of x. And I'm going to call that a whole new function. I'm going to call it uppercase f. And in this case, lowercase f is the sine of x, and then g of x is x squared. So our composition is the sine of x squared. Now we have the idea that as x changes, x squared changes. And then as x squared changes, the sign changes. So we've got that as x changes, g changes. And that's what we're looking at over here with g of x equals x squared. But then as g changes, g being the input of f, we can say f changes. So x affects g, which then affects f. Now that should all make sense, and this is basically the foundation of what is called the chain rule. And here it is. So we've got two functions that are differentiable, g and f, and then uppercase f is f composed with g. The derivative, f prime, for uppercase f prime, is the derivative of f times the derivative of g. Should make sense. I'm taking into account how lowercase f changes, how g changes, and the result is the product. Now about this g of x, it's because when I write down a derivative of a composition, what the outside function is holding isn't going to change. I'll come back to that in just a minute. Don't worry about it right now. First, I'm going to give you the alternative form of the chain rule. It's in Leibniz notation. So y is f, so the outside function, and u is g, and so the inside function. Then dy dx, that is, when x changes, the change in the outside function is the product of y changing when u changes and then u changing when x changes. These are saying exactly the same thing. We're not going to see a proof of this, and I don't want you to spend too much time thinking about what these symbols are saying right now. I mean, you maybe have been spending some time thinking about it, but we're going to just see how it works. So we're going to differentiate y equals the sine of x squared. The thing that tells me that I'm going to use the chain rule is that I have a composition, right? I have an outside function of the sine and the inside function of x squared. And so I'm going to actually identify the outside function is the sine, the inside function is x squared, and y prime is going to be a product. First, we're going to differentiate the outside function. The derivative of the sine function is the cosine. And I'm going to just let it sit cosine with empty parentheses for now. And then the derivative of the inside function, that g prime, x squared has a derivative of 2x. Now let's go back to these symbols. What this said was, if I have uppercase F is f of g of x, then when I differentiate uppercase F, I have little f prime of g of x. What this is telling me is the inside function doesn't change when I differentiate. And so since the sine function was holding an x squared, the derivative cosine is also going to hold an x squared. So the inside function doesn't change. So for something like y equals the sine of x squared, we will never, ever, ever, not ever write down that y prime is equal to the cosine of 2x. The sine changing to cosine is fine. X squared changing to 2x, absolutely not. That will never be the case. The derivative of x squared is coming out as a factor. Okay? Now I'm just going to rearrange this just a touch. So y prime is equal to 2x times the cosine of x squared. And that's it.